Thank you. I'd like to thank the organizers for their kind invitation. And today I'm going to talk about a model of black holes proposed by Hawaiians collaborators. This is the list of main references. And I believe that the information loss paradox can be resolved in this framework of models. Let's start by recalling a counterintuitive feature of the conventional model of black hole. So say we have a black hole over there, and if it's a classical black hole without Hawking radiation, it has a constant Schwarzschild radius, and if we throw some particle toward the horizon, we know that although it takes only finite proper time for the particle to cross the horizon, for us at distance, we see that it takes infinite time to cross the horizon. Now suppose we turn on Hawking radiation so that the Schwarzschild radius shrinks with time. Intuitively or naively, we would expect the particle to take longer time. It would be harder for the particle to cross the horizon because the horizon is shrinking. However, the conventional model of black holes tells you that actually it takes only finite time for a distant observer to see the crossing of the enfolding particle to cross the horizon. But this is telling you that in the conventional model, people choose a particular state configuration at the horizon, which is the same as the horizon state without Hawking radiation. So the Hawking radiation only exists at a distance, not at the horizon. On the other hand, today we know that this is not a consistent choice, because if you make this choice even, say in the beginning, later on there will be firewall, or there will be loss of information. So we would like to explore other choices for the configuration at the horizon. Before we do that, a related widespread misconception is this. I often hear people saying this. They say that we know for a classical black hole, infalling object crosses horizon in finite pocket time. And if we deform the classical black hole a little bit, say by a very weak radiation, then it induces a very weak back reaction. You would still have infalling particle crossing the horizon within finite time. To show that this is a misconception, I just have to give a counterexample. An example of arbitrarily weak radiation with the back reaction taken care of, and show that all infalling trajectories do not cross a horizon in finite time. So this is the example. Consider the outgoing Weyl metric for outgoing radiation. This is a solution of Einstein's equation. You have a Schwarzschild radius A, which is 2 times the bounding mass. If A is a constant, this would be just a coordinate transformation of the standard Schwarzschild solution, and little u is the Eddington-Mitali time. According to Einstein's equation, you have the energy momentum tensor. And for outgoing radiation, your Schwarzschild radius should be shrinking. So the time derivative or u derivative of A would be negative, and you have a positive outgoing like radiation. For very weak radiation, you have a Schwarzschild radius A that's almost constant, but with a very small negative first derivative. According to this metric, you have the light-like geodesics for the outgoing and ingoing light-like rays. And you can easily plug this into your computer and check what happens to the ingoing trajectories of massless particles. Of course, if all massless particles do not encounter any horizon in finite time, it's impossible for massive particles to cross horizon in finite time either. So we only need to look at the massless particles. This is the result of a simulation. Here we choose the Schwarzschild radius A to follow the trajectory as ordinary black hole. And to show the complete figure, I have to choose A to change rather quickly, although the same adjective feature persists even if you change A in other ways, as long as it's decreasing constantly. Now, if you have a particle initially outside the structural radius, you see that in the beginning it approaches to the structural radius quickly, but it stays outside structural radius until the structural radius goes to 0. As long as you have finite outgoing radiation, eventually the whole thing would radiate away. Say if A changes by 1 part in 10 to the 100th over a period of time of 10 to 100 years, over 10 to 200 years, the whole thing evaporates away. The outgoing Bayesian matrix becomes the Minkowski matrix, which is geodesically complete. So I enlarged this part, and you see that as time goes on, the particles outside the structural radius continues its trajectory into the Minkowski space. And all these trajectories are now geodesically complete. And through this journey, there is no crossing horizon. And therefore, you can see that even though you turn on only a very weak outgoing radiation, suddenly incoming particles cannot cross horizon within finite time. You may think that this is an artificial result because of the simulation, but we actually can write down an analytic proof. The proof is very simple. You consider the trajectory of the structural radius, and you plug it into the metric for the outgoing Bayesian metric. And you see that this trajectory is actually space-like, meaning that the structural radius is always shrinking faster than light, as long as the structural radius is shrinking. So if there's complete evaporation, assuming that A dot is finite, all the time, eventually the whole thing evaporates away, and outgoing Bayesian metric becomes Minkowski, which is geodesically complete. All the causal trajectories must be left behind the shrinking structural radius and speed faster than light. So there's no chance for any causal trajectory to cross over the horizon, and therefore you don't see a black hole apparent horizon in this geometry. But to many people, this is obvious. On the other hand, this is indeed an example telling you that the misconception is indeed a misconception. And note that here the argument only relies on the fact that I have outgoing radiation. A dot can be arbitrarily small. So even though you turn on arbitrarily small outgoing radiation, it's impossible for any inflowing particle to cross horizon within finite time. The geometry behind is actually like this. This is half of the Penrose diagram for a maximally extended structural solution. It has both a white hole horizon and a black hole horizon. Suppose you deform the geometry a little bit such that the horizon shrinks with time, so it's a apparent horizon now. You see from the diagram that the white hole horizon becomes a space-like apparent horizon, and the black hole horizon is now time-like. Since we have a space-like apparent horizon in the outgoing Bayesian metric, it's clear that the structural radius in the outgoing Bayesian metric is actually an apparent horizon for the black hole. And that's why it's impossible for any inflowing trajectory to cross the horizon. Of course, you can consider the opposite situation, consider the ingoing Bayesian metric, and get the opposite conclusion. So actually, the structural solutions degenerate. It's analogous to critical phenomena. Actually, people study gravitational collapse as critical phenomena. It's analogous to having a cup of ice. If the temperature is exactly 0, you can have coexistence of ice and water. If you turn the temperature just a little bit over 0, you get only water. And therefore, it's not okay to ignore the back reaction of even the smallest radiation. So now it's time to introduce the KNY model. proposed by Kawai, Matsuo, and Kokura in 2013. They made assumptions of spherical symmetry for simplicity, and they also assumed that there is only massless particles in Hawking radiation. They considered the gravitational collapse of a sphere of particles and assumed that it's only massless particles in this collapsing sphere, so that everything's collapsing at the speed of light. This is like the extreme case of gravitational collapse. If any gravitational collapse can lead to the emergence of horizon, you would think that this would be one of the cases. And here, I call it pre-Hawking radiation or Hawking radiation because I will show that actually in this model there will be no horizon either. On the other hand, when the surface of the collapsing sphere approaches to the Schwarzschild radius, for long wavelengths modes in the Hawking radiation, we shouldn't be able to tell the difference whether you have the surface of the collapse at the Planck scale outside or inside the Schwarzschild radius. So you still expect Hawking radiation. I'll have more to say about this. This can be checked by the Golubov transformation as usual. But let's first assume that we do get some outgoing radiation, even before the horizon appears. The main difference between this model and the conventional model is that here we do not assume that at the horizon or at the surface of the collapse there is no Hawking radiation. We assume that the Hawking radiation you see at distance can be extrapolated back to the surface of the collapsing sphere. So it's a naive assumption. People didn't consider this case. Actually, in the old days, people argued a little bit about why you shouldn't consider this. But I will say that those are also based on some other misconceptions that I'll mention. But let's first just go ahead and check what happens if we make this assumption. So first we focus on the geometry outside the collapsing sphere. Let's take capital R to be the coordinate of the surface, outer surface of the collapsing sphere. And assume that in the beginning it's larger than the Schwarzschild radius. So the Schwarzschild radius doesn't really give you a real horizon in the beginning. It's hidden beneath the surface of the collapse. Now, the geometry outside the collapsing sphere will be given again by the outgoing light dielectric because outside the collapsing sphere there is nothing but outgoing Hawking radiation. And so the equations are the same as those we saw before, but we're just applying to this ingoing geodesic equation to the outer surface of the collapsing sphere because of the continuity of metric. So the coordinate capital R of the outer surface of the collapsing sphere follows this equation as everything on the surface collapses at the speed of light. And then what we said earlier when we tried to clarify the first misconception, those arguments can be applied again to show that capital R, the surface of the collapse, never goes smaller than the Schwarzschild radius, and therefore you never really get Schwarzschild radius outside the collapsing sphere and give you a horizon. So there is no horizon throughout this collapsing process until the whole thing evaporates away and you have no horizon and all the informal trajectories are geodesically complete. And since throughout this time the radiation happens at the surface of the collapse, so you have local interactions to transfer information from the collapsing particles to the outgoing radiation, and therefore there will be no information loss. And since there will be no horizon, some people say it would be no longer appropriate to call them black holes. So I'll call them asymptotic black holes. With different initial conditions, eventually you get very similar final states. I'll talk more about that later. This is a consistent approach in the sense that in the beginning we made a different assumption about the geometry or the quantum state at at the surface of the collapsing sphere, different from the conventional approach. But in the end, we check that this assumption gives you a geometry that allows you to do oblique transformation to determine the Hawking radiation and plug it back into the equation we start with and check that everything is consistent. We will also check other consistency checks, whether you get a high intensity energy flow at the surface of the collapse, and other questions like we already said that you no information loss, so that's the first good thing. Now I'm not sure, but I guess most of you would have a lot of questions in mind right now, or thinking that I'm going wild. But let's first make another comment to try not to be misleading. First of all, there's no information loss paradox, not just because there's no horizon. Even if there's horizon, this picture would tell you that there will be no information loss paradox. What's happening is that if you look a little bit more into the details of the collapse, whenever something is collapsing, it would never enter the Schwarzschild radius defined by all the energy enclosed on this surface. And even if there is a pre-existing black hole horizon inside, this collapsing shell would radiate away before it enters the new horizon. And therefore, the radiation, the Hawking radiation, takes away information from the surface of the collapsing spherical shell. It's just like peeling off an onion. And therefore, this whole process is not too much different from the burning of ordinary matter. Although deep down, all interactions are quantum, and here maybe what's special is that Hawking radiation involves a quantum tunneling process. But at the macroscopic scale, we have a classical energy flux where it's going into Hawking radiation, just like burning anything. And also, of course, in observations, we do find a lot of candidates of black holes. This is not in contradiction with the observations, because whenever the collapsing surface is very close to the Schwarzschild radius, it would look extremely black. Okay, so why did people not consider this naive scenario? Well, they worry that if you really have Hawking radiation near the surface of the collapse, as the surface of the collapsing sphere approaches to the Schwarzschild radius, there will be a large blue shift factor that seems to be approaching to infinity. And you multiply this factor to the Hawking radiation, you get a divergent energy flux. In order to avoid this divergent energy flux, people chose the geometry at the horizon to be free from Hawking radiation. However, you can just go ahead and do a straightforward calculation to check whether this is right. Well, the point is that you can, for the KMY model, you have the radius of the collapsing shell following the ingoing light-like geodesic equation, and also you can use your Hawking radiation formula to determine how fast the Schwarzschild radius changes with time. Although here, actually, the precise formula is not really very important. In any case, you can use these equations to rewrite the outer radius of the collapsing shell as Schwarzschild radius plus a very small term. In this case, you get a constant 2 times sigma over A, where sigma is n times some constant. N is the number of species of massless fields. Therefore, you see that as the Schwarzschild radius changes very slowly for a large asymptotic black hole, you would see the surface of the collapsing sphere staying outside the Schwarzschild radius, always at this coordinate difference delta r, which is 2 sigma over A, which is a very small number. But small number would prevent the blue shift factor to diverge. And you really do a calculation for an inflow observer with a certain tangent vector, you see that the energy density observed by this involving observer is actually proportional to 1 over a squared. And therefore, for a large terrestrial radius, this is a very weak energy. And therefore, even though we didn't assume the surface of the relaxing sphere to be vacuum, when you are there measuring, doing experiments, it would be as if it's a vacuum state because the energy density is so low. Okay, so now comes to the question of Hawking radiation. Do we really get Hawking radiation or pre-Hawking radiation in the absence of a black hole apparent horizon? You can do a global transformation, and a generic scenario was done in a series of papers, including this one. What they pointed out was that what you need to get a Hawking-like spectrum of radiation out of oblique transformation, whenever there is an exponential relation between the defined parameters at past infinity and future infinity. And also, you have this physical argument that I gave earlier, and therefore you do get Hawking radiation or Hawking-like radiation or pre-Hawking radiation, even in the absence of horizon. You may even wonder, now, at least in the past, you have the black hole apparent horizon in proximity. Now you have the white hole apparent horizon in proximity, hidden beneath the relaxing sphere. How can you get Hawking radiation? Well, actually, when you really do the oblique transformation, you see that the result is different. The oblique coefficients differ from the old calculations by complex conjugations corresponding to the time reversal transform. But the creation of particles depends only on the absolute value, so you get the same spectrum as Hawking radiation. And what I said above, although sounds like it applies only to a special case of masses thus collapsing, spherical symmetry, etc., but you can generalize the conditions. You can consider incomplete evaporation, assuming that the formula of Hawking radiation is modified at different scales. You can consider more generalized configuration of collapsing matter. You can consider more general components in Hawking radiation. And you can show that the arguments would in general go through. They are robust. I have not yet talked much about geometry inside the collapsing sphere, but you can study it in the following way. You decompose this collapsing sphere into infinitely many infinitesimally thin shells, separated by infinitesimally thin layers of space in which there is nothing but outgoing Hawking radiation. And using spherical symmetry, you know that you can apply the outgoing radial metric in every one of the infinitesimal thin layers of space. And then you can apply what we said above about outgoing radial metric and take the limit. And therefore, you can actually write down the metric for the geometry inside the collapsing sphere. And then you see that there is a huge redshift for information deep down below the surface of the collapsing sphere. And that's why when you have Hawking radiation, it takes away information from the surface of the sphere. What's below the surface of the collapsing sphere is further frozen than the degrees of freedom at the surface. And this also gives you an intuitive understanding of why the information for a black hole appears to be residing on the surface. So putting everything together, when we have the space outside the collapsing sphere covered by the outgoing radial metric, we have apparent horizon by energy continuation. And then we can decompose the collapsing sphere into many layers and consider the outgoing radial metric in the space between layers. And you put everything together, you find that the parallel diagram for the KY model is the same as that of the Minkowski space. Now, the concept of asymptotic black holes is a byproduct when we solve the information loss paradox. I mentioned that the surface of the collapse will stay outside the Schwarzschild radius at this coordinate difference. You can apply this result for every layer inside the collapsing sphere. And also this is reminiscent of what people said about brick wall model and network paradigm. Although in those cases, you have the imaginary grain or wall outside the Schwarzschild radius, but here you have the physical collapsing sphere composed of matter. So it would be interesting to see what are the statements that would persist and what are those that would be modified. And also, you know that the Tsinghua model that's often used in discussions about black holes is actually not reliable. Because however thin the initial state is, the inner surface of the collapsing spherical shell would reach the origin very quickly over a time scale of n. But the outer surface of the shell would stay outside the Schwarzschild radius. And therefore, in the end, you always get a thick shell or a solid ball. Of course, there are earlier papers in which people consider black hole models without event horizon, but often they still have a tracking region or apparent horizon, and we don't have it. And also there are other studies based on particular models of field theory or particular models of dynamics inside a collapsing star, or it's based on string theory or high energy theory. So what's new here is that this is a robust argument based only on semi-classical physics. So let me go to the conclusion, because I have no time. We have a consistent model of black holes. We check consistency of the model, although I limit my time, so I can't go through all of them. It's based only on semi-classical large-scale physics, where we don't get any problem like firewall. And if there is not horizon in the initial state, there will be no horizon in the end. There's no information loss paradox, although you might want to go ahead and see the final version of this model and check accuracy. But there is no paradox in the beginning because all the information can be transferred locally from the matter to the Hawking radiation. And finally, we get a picture of symptotic black holes, assuming there is no CMB, assuming that background temperature is 0. We have only outgoing Hawking radiation, and then black hole final states will be similar in the way I described earlier. Thank you.
Time for a few questions.
The Oppenheimer-Schneider solution from the 30s shows clearly that there is a region that shows clearly that the time to get to the singularity is finite, and that there is an interior region where all points end up at the singularity. Now, we know that semi-classical corrections are a small effect, and therefore this region will continue to exist. So I think that argument is completely clear and solid. So I think if you are getting something different, it must be doing something wrong.
Yes, I forgot to mention I do have a singularity at the origin. But the information loss is concerned with, I'm talking about the original information loss paradox for low energy physics. You can consider string theory or other high energy modifications to resolve singularity. But at this stage, we do have a singularity at the origin. So it's not a contradiction.
Okay, I think the problem is that one can't model an evaporating black hole using an outgoing Beijing metric. If you look at the Raychaudhuri equation on the horizon of the black hole, there's no flux of energy crossing the event horizon if you have only outgoing null radiation. So I think what your analysis is really looking at, in outgoing Vijay coordinates, the horizon you pick out is the white hole horizon.
Right.
And then the fact that ingoing null GD6 never cross the horizon is simply what we would expect, since they don't ever enter the white hole. So I think there is a problem with trying to use outgoing Vijay metrics to say anything about evaporating black holes.
Right, so I don't really have a white hole, so, and the outgoing Vijay metric applies only outside the Planisphere. So I'm assuming that I have a well-defined sphere of radius r. Outside this radius, there's nothing but outgoing quantum radiation. So I'm only applying the outgoing Vijay metric outside this region, not inside. Inside, I had to do what I mentioned earlier, dividing the sphere into many thin shells and get a totally different metric.
Okay, maybe we should talk about that.
If there are no more questions, let's have a speaker again.